Hi, I'm Joe James, and in this video I'm going to give you an introduction to Python NumPy arrays. NumPy is a high-performance, multi-dimensional array library in Python that's primarily used for numerical analysis. So you may be asking, why would I use a NumPy array when I can just use a list? Well, you're right, lists are very flexible and versatile, and it's a really great data structure in Python. But there are a few advantages of NumPy arrays. So one, they save you coding time. You don't have to iterate through an array to apply a mathematical operation to each element of that array. You can do it with a single line of code. Let me show you a quick example of that. Using a Python list, you have to use a for loop to iterate through that list before you can multiply a times equals 3 operation to each element. And using a NumPy array, you apply that element directly to the entire array with a single line of code. NumPy takes care of the rest of the operation behind the scenes, so you don't have to worry about it. And it also executes faster, much faster, because it uses a single data type for each element in the array. Now, it's less flexible because of that. Every element has to either be a float or an int, but they all have to be the same data type for each element in the array, so it avoids type checking at runtime. The NumPy array also uses contiguous blocks of memory, and I'll show you what I mean by that in a second. The NumPy array uses less memory than the Python list. Here's why. A Python list is an array of pointers to Python objects that are stored somewhere else in memory. They're scattered around in memory. So it has a list of pointers which themselves each take up 4 bytes, plus the object which is stored in memory, which has metadata associated with each object. The NumPy array doesn't use pointers. The type and item size are the same for each column in the array. And it also has these really compact data types like unsigned int 8 or float 16, depending on what you're trying to do and how much precision you need in your data. So let me explain this graphically. So in a Python list, you have a block of memory addresses, but at each memory address there's only stored a pointer. Not the data itself, but a pointer to the data at another location in memory. So when you follow that location, you find one piece of data only, not the entire array there. One piece of data is stored there. And if it's, for example, a float, then it needs to have metadata associated with that. So there's 8 bytes for the float, plus it needs the space to store the item size, the data type, and other metadata. So there's actually a lot of memory used up, and execution speed is slower because of this dereferencing of the array. And then a NumPy array is different. It stores the memory address and the data in a contiguous block of memory. So if it wants to iterate through the array, it does it very easily without having to dereference these memory pointers. So some of the metadata associated with NumPy arrays, you have the data type, and you have item size, or how many bytes that item takes up in memory, the shape of the entire array, and the data itself. And the easiest way to access the data is using indexes, similar to what you do in lists. So some of the data types in NumPy, they're very similar to Python data types, but not identical, and there's a reason for that. So of course, Boolean integers, you can have 8-bit or 16-bit or 32-bit or 64-bit integers. The reason for this is that if you only need, let's say, numbers between -128 and +127, you can use an int 8 and you can save a whole bunch of memory. It uses only 8 bits of memory, or 1 byte. Int 16 uses 2 bytes of data. Int 32, 4 bytes of data. And int 64 uses 8 bytes of data. So depending on how much precision or how large your numbers are, you can use a different data type in a NumPy array. And then you also have unsigned integers, and you also have different precision levels of floating point value, from 4-byte or 16-bit up to 8-byte or 64-bit. In Python lists, they always default to a float 64, which uses 8 bytes of memory. If you don't need that precision, you can use float 16, and for larger data arrays, you're going to use up a lot less space in memory. And the reason for that is that if you don't need a whole lot of precision, or if you have a really huge array, you can use a less precision or smaller data type that only uses up 2 or 4 bytes of space per element. And you also support complex numbers, which have both the real and imaginary components to them. so 64-bit and 128-bit. It also supports Boolean, string, date time objects, and regular Python objects as well. Now let's go to the command prompt and try some NumPy commands. First, let's make sure you have NumPy installed. You want to do pip install NumPy if you're using pip for your package manager. And you can see I already have it installed. That's the easiest way to install it. You can also do pip install NumPy -- upgrade to make sure that you have the latest version of it installed, which I already do. I've already updated mine, so I'm not going to run that, but -- upgrade if you want to upgrade your NumPy to the latest version. So if you have NumPy installed and running, what you want to do is jump into Python. So we'll run the Python command. Now we've got our Python command prompt, and we can do import NumPy as np. That's kind of the standard of how people import NumPy. So we'll use np dot when we call a NumPy function. Now let's look at different ways that we can create a NumPy array. We can start by just passing in a list. So we can say a equals np.array, and then we have parentheses, and then inside those parentheses we're going to pass in a list, which means square brackets, 2, 3, 4. That will give us a NumPy array A with 3 elements in it. So that's one way, is just to create a NumPy array by passing in a list. You can also use the aRange function. This is a NumPy specific function that does range from 1 to 12 and a step of 2, so it's very similar to the range function. And we can see that A has 1, 3, 5, 7, 9, and 11 in it. So the range function is a very easy way to create a NumPy array. And in this case we have integers. And one more quick easy way to create an array in NumPy is to use the linspace function. This is linear spacing from 1 to 12. And this is not step, this is the number of elements. Linspace creates a floating point array. So from 1.0 to 12.0, that will be the first and last elements of the array, and it'll have a total of 6 elements. So let's take a look at that. So that's our array that are evenly spaced, and this is just a one-dimensional array, evenly spaced 6 elements. Now if we want to reshape our array into a 2-dimensional array, we can use a.reshape. And here let's try and reshape it as 3, 2. So you can see we have 3 rows of 2 elements each. However, we didn't save that to A. If we want to save it to A, we can see that our A array is still just one-dimensional with 6 elements. We'd actually have to type A equals a.reshape 3, 2. Now we've saved those changes to the variable A. So that's the reshape command. Let's look at size. We can get the size of the array, which is the number of elements in the array. And size doesn't care what the shape of the array is. It's just going to tell you how many elements are in the array total. And here we have a 6-element array. We can also get a.shape. You'll note size and shape are not functions. They don't need parentheses after them. So a.size is a variable, and you're just showing the value that's stored in that variable. A.shape is 3, 2. We already know that. And we can also get data type. So let's look at a.dtype. And it's float64. So that is a NumPy data type. It's an 8-byte or 64-bit data type. And that's the default for floating point values in NumPy, also in Python. You can use lower precision floating point values, of course, as I showed you earlier, but the default is 64 bits. So now when we look at a.item size, that will tell us how much memory in bytes each element of the array takes up. We already know that since this is a float64, it's going to be 8 bytes, 8 bytes of memory. It's important to understand how the brackets and parentheses work. If we use np.array, first you have to have an outer set of parentheses around it. Then you need to pass in a list, which is going to be inside of square brackets. Now if you want to create a multi-dimensional array, you don't need to use internally square brackets inside of those outer set of square brackets. You can just use parentheses, comma, and then another set of parentheses. So this will create a 2-dimensional array. But you'll see that this, with no square brackets at all, doesn't work. That gives us an error. Another little trick we can do is a less than 4. So we have this array, two-dimensional array, and we want to compare each element of the array to 4. And we do that with just 3 characters. So easy. And it actually runs this operation on every element of the array, and it returns a true or false, a Boolean response for us. And if we want to multiply each element of the array by an integer, let's say 3, a times 3. That multiplies each element of the array by 3. Again, we didn't save that, so if we want to save it, we have to say a times equals 3. Now we can see the values are saved, but we multiplied every element of the array by 3 with just 4 characters. So really easy, efficient way to perform operations on the entire array using NumPy. In regular Python using a list, you would have to write a for loop, you'd have to iterate through each element of the Python list, and then perform this mathematical operation on each element one by one. And if we want to create an empty array but full of zeros, we can do this. np.zeros gives us an array full of 0 values. Again, these are all floating point values, and they're defaulted to float64. So if we do a.dtype, we're going to see that these are float64. We can also create an empty array full of 1s. We use np.ones. So here's how we can do that. And we can put in any shape we want. A. If we want to set a equal to a one-dimensional array of 1s, we can do np.ones. And then we can pass in how big we want it to be. So if we want 10 1s, we can just do that. A will have 10 1s, and all are going to be floating point values. Optionally, you can pass in parameters. Here we can pass in a parameter of data type. So we want the data type to be int16. So it uses up less memory. So here's our new array, and we can see the dtype is int16. And if we do a.dtype, it'll also show int16. And if we do a.itemSize, we can see these are only 2 bytes each. So it's very efficient in memory space. So you just pass in this dtype equals np dot, and then the data type that you want. NumPy has a random function, so we can create an array full of random values. Here we're going to pass in the shape 2 and 3. So we'll have a random array. And the random values are going to be ranging from 0 to 1. So they're floating point values. If we use random.random, it's going to give us 0 to 1. Now let's say we want to print this out, but we don't like showing this many decimal places. We can do np.setPrintOptions. And this will set the print options for all future print statements until we revise this. But we'll say the precision is 2, in other words, only show 2 decimal places. And suppress equals true means sometimes NumPy will default to showing scientific notation, but we don't want it in scientific notation. So let's take another look at A, and we can see there are 2 significant figures there. And if we want an array of random integers, we can say A equals np.random using the NumPy random function, and then it's going to use randint from 0 to 10 inclusive and 5 elements. So let's take a look what A is. There are 5 elements there. We have some mathematical or statistic functions. We can use a.sum. We need to use parentheses to call these. 25. Let's scroll down a little. a.min. 1. a.max. It's going to be 9. a.mean. 5. a.average. Average doesn't work, so we're going to use mean to get the average. a.var, if you want the variance. 11.6. a.std, if we want the standard deviation. Standard deviation, std, 3.4. So here's another trick we can do. Now let's create a new random array of integers with 6 values in it. And let's reshape that to 3, 2. So that's what our array looks like. Now we want to get the sum of only axis 1. So we can type a.sum and we can pass in this argument axis equals 1. So that's going to apply the sum of axis 1. You can see 8 plus 3 is 11, 4 plus 5 is 9, and 8 plus 3 is 11. So it's giving us the sum of axis 1, or in other words this axis, these pairs. We could also pass in axis 0 if we wanted to just get the sums of the 0 axis, which would be the vertical columns here. 3 plus 4 plus 3 is going to give us 10, 8, 5, and 8 is 21. So you can get the sum of a vertical axis or a horizontal axis, whichever axis you want. You can also use this axis equals for any of those mathematical functions, the statistical values that we just looked at, like standard deviation. If you want standard deviation by a column, you can do a.std and then axis equals. So another nice trick is we can import a text file or a CSV file with a single line of code. So here we'll assign this text or this the CSV data to this variable data, and we'll do np.loadText. This is the easiest way to do it, although it's not the best. Load text will load in the data.txt file, that's the file name, and then we can say dtype. Well, we can use the default if we want to, which is probably going to be float 64. In this case, I want to use unsigned integer 8, so it takes up less space. It's going to be just 1 byte per value instead of 8 bytes per value. And then a delimiter of comma, because this is a comma separated text file, and skip rows. I have a header line that I want to skip. I don't want to try and convert those to floating point values or integers. So I'm going to skip the first row, and that's really all you have to do. 1 line of code to import the text file. Now we have a nice big array of integers with unsigned int 8. And these are all just random values from 0 to 10, 0 to 9. That's why I was able to use the unsigned int 8 for this. So depending on what type of data you have, you may not want to just use the default of float 64, depending on how big your array is. And note that this doesn't really handle exceptions very well, so if you have missing values or something, or some random characters mixed in, letters or something, it's not gonna work very good. You don't really handle exceptions using the load text. So you might want to use gen from text instead. That's gen from txt, and you can check that out and read up on the docs online. It handles those types of exceptions a lot better for missing data and things like that. But load text is a nice easy way to load in text if you have well formatted data in a text file. I'll show you a couple more tricks here. So let's create a range of 10 values, 0 to 10, using the aRange function. And then we can randomly shuffle these, put them in random order using np.random.shuffle. And we pass a in as the argument. And now we can look at a and we can see it's in random order. Now you don't want to use a equals here because this is an in-place shuffle. Just like the sort function is in place, the random.shuffle is also in place. Another one we can use is np.random.choice of a, and that will give us a random choice. It just randomly picks one, and if we run this multiple times, it'll give us a different item. So it'll give us a different item each time. It randomly chooses one, random.choice. And then we can also do, I think I already showed you the random integers, but let me show you that. So this goes from 5 to 10 range and 2 items. So I hope this was helpful for you. I'll post a set of commands I use in a text file on GitHub, so you can try out some of those commands. This is far from comprehensive. There are so many other different functions in NumPy that are very powerful, useful functions, and there's no way I can cover all those in one video. But I wanted to give you an introduction to NumPy so that you know some of the basics. You can start using it, you can learn to use it, and feel comfortable with it and understand the benefits of NumPy. I hope this video was helpful for you. If so, please click the thumbs up and subscribe to my channel. I'm Joe James. Thanks for watching.